Hi all. This is just a quick video to kind of emphasize even more that idea of the relationship between the graph of a function and the graph of its inverse. So I do have a function that I'm starting with here. Oh shoot, I changed my color in the last video. Give me just a sec. Make this blue. Okay, so I'm starting with this h of y equals -1 over y. And I'm supposed to find h inverse of y, and since I'm given a formula, I'm going to assume that that means find the formula for the inverse. This actually is a nice one for reasons other than the graph part as well, because my independent variable is y, and that can really mess with people. So I just want to point out that an option is you could also just drop the function notation for now and say, oh, I don't know if I like that because I'm going to call it h inverse. We'll just use a different variable. We'll say z equals -1 over y. And then we want to switch our x and y, which in this case are our z and our y. So y equals -1 over z. And remember that we use z to represent the function. So when we get there, that's our inverse. So if I want to solve this for z, I'm going to multiply both sides by z. And I'm going to say yz equals -1. And then I can just divide both sides by y, so it's not algebraically a hard problem. And I get z equals -1 over y, which should be telling me that h inverse of y is equal to -1 over y. Which, interestingly, is exactly what I started with. So if you're skeptical, you can always check, right? You can say h of h inverse of y, or vice versa. They're going to look exactly the same. Is the same as h of -1 over y, which is h takes whatever you give it and gives you back the opposite reciprocal. So it's going to be the opposite reciprocal of -1 over y. So I can see that my negatives will cancel, and I have 1 divided by 1 over y. And remember that to divide by a fraction, you can multiply by its inverse, which means h of h inverse of y is y. So I did, in fact, get back where I started. So they really are inverses, meaning, interestingly, a function can be its own inverse. There's more than one that's true for. Not tons and tons, but there's more than one. And if we're thinking about graphs, this means that when you flip the graph over y equals x, you get the exact same graph, which means that this function, to begin with, was symmetric about y equals x, which is an interesting one. So we haven't studied, oh, well, no, I'm lying to you. We did the reciprocal function, y equals 1 over x, and this one is just flipped upside down. So it's going to look like this. Kind of rough. But if you think about that, if I put my y equals x in there, and you kind of see it, if I flip over that diagonal, it's going to land right back on itself. So it's odd as well. There's other symmetries. Try not to get those mixed in, but just visualize flipping this part across and it would land on this part and vice versa. So if a function is its own inverse, then its graph must be perfectly symmetric across y equals x. So just kind of an interesting little tidbit. Thanks for watching.